Quantum Insights: How Perturbations Affect Degenerate States in a 3D Harmonic Oscillator. Learn how first-order perturbation theory reveals the fascinating nuances of energy states under perturbation. In this problem, we're tasked with consider the isotropic 3D harmonic oscillator, discuss the effect in the first order of the perturbation H prime equals lambda x squared yz for some constant lambda on the ground state and the triply degenerate first excited state. So a pretty cut and paste or cut and dry problem, but we're going to have to invoke both degenerate and non-degenerate perturbation theory for the first order with our old friend, the harmonic oscillator. So why do we care? Well, I think as you've seen by now, the 3D harmonic oscillator is a fundamental and versatile model that provides deep insights into both the theoretical and applied physics. Again, think about the atom and molecules, where the nucleus is attached to springs and up, down, left, right, in and out of the board, and we see that it just kind of vibrates and oscillates there. So a 3D harmonic oscillator is actually really, really important. So the challenge for you is, what does this perturbation represent? Something like x squared yz, what would that represent? That's a kind of cool thing to think about. But this is a little, gets a little monotonous and tedious, so don't forget, check out the PDF using the link below. Free to all the members on the Patreon. Thank you for bringing us up to over 100. That's really cool. Love it and can't wait to see more, especially as we get into some of these other topics. If you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. Now, let's get into the fun. Alright, so in stop one then, well, if we're using a 3D harmonic oscillator, we can recall that from problem 4.46 that we were able to use separation of variables and replicate the ground states that were looking like the 1D oscillator. So we're going to use the 1D oscillator state 𝝅n, and that was done back in chapter 2, and we saw that we could replicate any of those states based on the ground state with the raising and lowering operator. So that was pretty cool. But now we're going to define this state, the zero state for the ground state, as some product of 𝝅0 x, 𝝅0 y, and 𝝅0 z. So that's what the separation of variables allowed us to do. So that's what we did in problem 4.46. Pretty cool. But now on to the real heart of the problem. We want the first order corrections to the new perturbation. So we have to take the expectation value of this ground state with the perturbed Hamiltonian. Okay, and that's what we see summarized here with the expectation value. So if we plug in everything, just to get our notation straight, we see that we have 𝝅n, which is n equals 0, so we're cool, and we just have all the variables, the perturbed Hamiltonian, all the variables, all in the ground state. And if we remember this expectation, the inner product and orthogonality, and the fact that these are represented by integrals, things of that nature, we can split them up into independent products thanks to orthonormality. So we get all x in 1, all y in 1, and all z in 1. And that's pretty darn cool. And then we can shorthand this to the expectation value of x squared in the ground state, y in the ground state, and z in the ground state. So pretty darn cool. And then we see here that, well, thankfully we have done this before in problem 2.12. So we know that the expectation value for x squared is n plus 1/2 h bar over m omega, but n equals 0 here, so we just have 1/2. And again, all of these equations are summarized in the beginning of the PDF, so go check that out. We also saw that the expectation value for the x's without any powers is the linear term, so any variable in the linear goes to 0. And that 0 is going to come back and save us a lot of time later. So since we have a product with the 0 in it, the whole thing goes to 0. And that is wonderful. And we see here quickly then that the total energy is the unperturbed energy of the ground state plus the first order correction But since that thing went to 0, we just have the first order energy state, which is 0 plus 1/2 h bar omega, so that's just 1/2 h bar omega. So this tells us that there's no change in the first order, and that's pretty darn cool. So we successfully get through part A pretty fast. Now we can move to stop 2, which is part B, the triply degenerate first excited states. Okay, so let's get this in the same notation. Use whatever notation you deem as reasonable. There's a lot out there. It's just the cats make it easy to move through, putting the subscript on the outside of the expectation angle bracket. Whatever floats your boat. I've seen plenty out there. I'm just trying to keep up with what this book does. But we see that by shifting the next, or shifting one of the wave functions up to the next level, we get a first excited state that has a degeneracy of 3. And we see that because there's 3 ways to get the next energy by 1, 1, 1, and the rest 0. So there's 3 ways to orient this energy. Okay, and hence triply degenerate. So now that we have our definitions here, we can apply the same process, but we'll have to now use degenerate perturbation theory. And that's where things can get kind of clumsy and messy because we have to deal with the W matrix. So let's see how we do that. Thankfully, we're given some equations here that tell us what the W's are. Okay, so this comes from equations for 740 and 741, where we have, since it's triply degenerate, we have a 3 by 3 matrix that we'll have to take the eigenvalues of later, and we see that each element in the matrix is the expectation value of a state with another state in the with the perturbed Hamiltonian. Again, triply degenerate, so that means that we're running through all 3 states and all their potential mixing pairs. And we know that we have a cool little trick here where if instead of having to calculate 9 components, I have to calculate 6 because I can switch the indices here as a result of my conjugate. Although, we can see we need to be careful there in doing so. But that being said, that saves us time, cute little trick, all the fun stuff there. So be careful, but also realize that this trick will save you time, especially when you're dealing with 4 by 4 or 18 by 18, like we did with the Zeeman effect. So very cool stuff there. But now let's get on to the fun. We're going to start with the main diagonal of this thing. So that would be all the same mixed pairs, i.e. 1 and 1, 2 and 2, 3 and 3. So everything is mixing with itself. Okay, that's where the heart of most of these come from. So we're just going to keep mixing with them. All right, so using the same notation and breakdown, we mix state 1 and 1 with the perturbed Hamiltonian. We break that down. We see that the only energy level or the wave function that got advanced was the one for Z. So we break it down, break it down, break it down into separate products, and we see that we get something useful here. We see that we get h squared or x squared of the ground state, y of the ground state, and z of the first excited state. But we see here that we don't need to do any further calculations because the ground state with y, or an independent linear variable, is 0. So since that's 0, the whole thing's multiplied by 0, and we save ourselves time and get rid of it. And that was the result of problem 2.12, which comes back over and over again. Let's see where it comes in again in the next slide. So with W22 now, we need the mixing state of 2 and 2. Do the same thing. Now the Y has the first excited state wave function. We see that here and here. Easy enough. Split it into its product. And then we get that we have x squared in the ground state, y in the first excited state. And once again, we have a z in the ground state, which we know goes to 0 thanks to our problem 2.12. So 0 again on the main diagonal. And I think you can guess it. Run it through the same thing with 3. You get 1 here, split it up. So now the x has the 1 on it, the x squared has the 1 on it for the first excited state, but the other 2 terms are 0 due to problem 2.12, and we get a 0. So all our main diagonal elements are 0, and that's going to come in handy when we have to deal with the fact that we're going to have to find eigenvalues. So let's continue and find the other 3 elements that we need. So now moving on to the first mixed state where we have 1 and 2. Okay, so we see here that in the shorthand notation that we've just become accustomed to, we have x squared with the 0, the our ground state rather, and then we have 1 and 2. But 2 had y as the first excited state, and 1 had z as the first excited state. So we see we have a 0, 1 and a 1, 0 here for the y and z respectively. And here's where we have to be a little careful. We get the expectation for x squared from problem 2.12, but we get the mixing pairs for expectation values from problem 3.39, okay? And that became very hefty to deal with because we had to make sure the indices on the Kronecker delta matched. So with this, we see that although we had n and an n prime here in the second bracket, and then we had n prime with n minus 1, then we had n and n prime minus 1. Again, that problem was pretty hefty to deal with, so just, if you want to look at that PDF, feel free. But what we see here is that since we have a 0 here in the radical, that thing goes to 0, and a 0 here in the radical, that thing goes to 0. But they would have gone to 0 anyways because of the Kronecker delta, which was 1 and -1. Those indices don't match, so that would have gone to 0. Thankfully, our Kronecker delta here is 0 and 0, so we get a 1 there. Then we have a 0 and 1 minus 1 is 0, so we get a 1 value there, so the 1 there. And of course, square root of 1 is 1. So we see those highlighted in the curly brackets. And now we just get to simplify. We have the green square root and the green square root. So there's 2 of them being multiplied, so the square roots will go to a square, and they cancel out, leaving us with just h bar over 2m omega. And then we see that from the x squared expectation, we get another factor of that. So that goes to a square. Pretty cool. And because we know that we can, mix my notation here, but because we know that this is equal to mixing and that W star is equal to 1 over 2, or 1, 2, since it's all real, we don't have to calculate that value for W21. And that's pretty tight. We like that. So moving on then, we do the same thing with W13 and W23, but we see that in the mixing states, we get this y with the 0 and z with the 0. And we know from 2.21 that both of those terms go to 0. So those elements go to 0. So now what we need to do is summarize this into one thing, and let's see what we get. All right, so here's our completed W matrix. We had 0 on the main diagonal, and then we only had 2 terms, the 1, 2 and the 2, 1, due to the conjugate, so that's nice, and then zeros everywhere else. So if we simplify this by making a substitution of xi, we see that we just get, 7 out of the 9 entries are zeros, pretty easy. Now we have to find the eigenvalues, and in this case, the eigenvalues are E1. So we just have to be careful again on the notation because lambda is given as a constant here. So using lambda for the eigenvalues is not a good idea. But evaluating the characteristic equation here via the determinant equals 0, we get this as our characteristic polynomial, and that leads to the roots of 0 and plus or minus xi. So the first order energy corrections for the first excited state is E1 equals 0, and then plus or minus the lambda with h bar over 2m omega squared. And that brings us through our second checkpoint, and that concludes this problem. Really not too bad, but I think what we see as a result of this is that we have something that depending on how the oscillations occur, lead to a big change because you have something really small being squared if we're looking at omega. So that could be something to consider. And of course, if lambda is, whatever constant it will be cooked up to be, that could also play a big factor. But pretty cool problem, and pretty easy once you just get a handle on what you need to do for the setup. Alright, so in summary, we got to visit our old friend, the harmonic oscillator. That was pretty cool. And then we got to see how a perturbation affected it in the 3D case. Nothing too crazy, I wouldn't say, after dealing with everything else in this chapter, but pretty nice to see our old friend coming back and just getting more practice with all the notation and the theory aspect of it. So a massive thank you goes out to my supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for access to supplemental material, current and future projects, and one-on-one help, especially as the new school year is starting to roll in come August. New content is posted weekly to fuel your curiosity. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.